Have you ever stopped to think about how some of the most complex, mind-bending ideas in the universe are really just built on the simplest patterns? Today, we're going to dive into one of those patterns, something you probably learned in grade school, but I bet you never realized was a key to unlocking the secrets of prime numbers and even keeping our digital world secure. Our story starts, of all places, in a German classroom way back in the 19th century. The teacher, trying to get a moment's peace, gives the class a ridiculously tedious task: add up all the numbers from 1 to 100. So while all the other kids are hunched over their slates, scribbling away, one boy just stands up and gives the right answer. 50-50. That kid was none other than the future legendary mathematician Carl Friedrich Gauss. And the incredible trick he used? Well, that's the heart of everything we're talking about today. All right, so here's where we're headed. First, we're going to nail down the basic idea, that simple, constant step. Then, we'll grab a super useful tool for finding any term in one of these sequences. After that, we'll unpack the genius summing trick that Gauss used. We'll also see how these patterns stack up against a couple of others. And then, the grand finale. We'll see how this simple idea explodes into the world of advanced math, from prime numbers all the way to modern computer programming. Okay, first things first. What exactly is this pattern we keep talking about? It really all boils down to one simple idea: a constant step. So an arithmetic progression, or AP for short, is basically a sequence of numbers that's super predictable. Think of it like walking up a staircase, where every single step is the exact same height. You're just adding the same amount over and over to get to the next number. And that fixed amount we add each time, we call that the common difference, or just D. Let's make this real. Take a look at this sequence: 3, 7, 11, 15, 19. You see the pattern, right? To get from 3 to 7, you add 4. To get from 7 to 11, you add 4 again. It's that constant rhythmic step that makes it an arithmetic progression. For this example, our common difference is a positive 4, and that's the whole magic of it. That step size never changes. It's perfectly consistent, perfectly predictable, and that predictability is what makes these sequences so powerful. Now, because these progressions are so predictable, you don't have to write out the whole long list if you want to find, say, the 500th term. We can just use a simple formula to jump straight there. And here it is, the secret sauce. To find any term, which we call an, all you do is take the very first term, a1, and add the common difference, d, a bunch of times. How many times? n-1 times. Now, you might ask, why n-1 and not n? Well, think about it. You're already standing on the first step. To get to the 10th step, you only need to take 9 more steps. Makes sense, right? Let's try this out with a new sequence. 2, 6, 10, 14. The first term, a1, is 2. The common difference, d, is 4. And we want to find the 20th term, so n is 20. We just plug it in. It's 2 plus 19 times 4. Well, 19 times 4 is 76. Add the 2, and bam! The 20th term is 78. No need to write out all 20 numbers. Okay, so let's get back to young Gauss. How did he sum all those numbers from 1 to 100 so ridiculously fast? He didn't have a formula memorized. He used something much more powerful: pure logic. So, check out this elegant thinking. He pictured the list of numbers 1 to 100. Then he paired the very first number with the very last one. 1 plus 100 is 101. Then he did the second number and the second to last. 2 plus 99? That's also 101. And this pattern keeps going all the way to the middle. Every single pair adds up to the exact same number. Since there are 100 numbers, that's 50 pairs. So all he had to do was multiply 101 by 50 to get the answer, 50-50. It's just so brilliant. And Gauss's amazing trick is exactly where we get the general formula for summing up any arithmetic progression. The total sum, Sn, is just the number of pairs, which is n divided by 2, multiplied by the sum of each pair, which is always the first term plus the last term. It's his exact logic, just turned into a formula we can use anytime. But hey, what if you don't know what the last term is? No sweat, there's another version of the formula for that. All we do is substitute our first formula, the one for finding any term, into this one. It gives us a new formula that only needs the first term, the common difference, and how many terms there are. Super handy. Now, to really appreciate the simple, steady beauty of an AP, it helps to see what it's not. You see, arithmetic progressions aren't the only way to build a sequence. There are other patterns out there, and they behave very differently. This table lays it out perfectly. Arithmetic progressions, or APs, they use addition. That gives you steady, linear growth. But a geometric progression, or GP, uses multiplication, and that leads to explosive, exponential growth. Think of a viral video. Then there's the harmonic progression, or HP, which is kind of the weird cousin. It's a sequence made from the reciprocals of an AP, and it actually decays, getting closer and closer to zero. Okay, so we've got the basics down, but this is where our story takes a wild turn, from a simple classroom trick to the absolute cutting edge of modern research. It turns out that this simple pattern of taking constant steps is a fundamental building block in some of the most advanced parts of math and computer science today. A huge part of this is a field with a fancy name, additive combinatorics. But don't let the name intimidate you. Professor Luca Trevisan from UC Berkeley explains it pretty simply. It's all about finding patterns in sets of numbers that behave in a linear way. And, as we've just seen, APs are the definition of a linear pattern. What this field is really asking is a profound question. If you have a big enough set of random-looking numbers, are you guaranteed to find certain structures hidden inside? It's like looking for order in chaos. And the simple arithmetic progression is one of the most important structures they hunt for. And the discoveries coming out of this are just mind-blowing. Get this, the Green-Tau theorem proved that even inside the prime numbers, which seem totally chaotic, you can find arithmetic progressions of any length you can imagine. A deep, hidden order. And in computer science, these ideas are used to test massive data sets. Instead of checking every single piece of data, algorithms can just sample it and look for these AP-like patterns to verify the whole thing. It's an incredible shortcut. And all of this even plays a role in cryptography, helping us create number sequences that are unpredictable enough to keep our information safe. So let's bring this all home. That simple, constant step, the pattern that a 10-year-old kid noticed in a boring classroom, it's not just a cute story. It's a fundamental key to the universe of numbers, a key that helps us find secret patterns in the primes and helps build the secure digital world that we all depend on every single day. It really makes you wonder, doesn't it? We went from a classroom trick all the way to the frontiers of modern math. What other simple, everyday patterns that we walk past without a second thought are hiding secrets just as profound, just waiting for someone to notice?